Hello, and welcome back for another discussion and demonstration of the implementation of Holt Winters forecasting method. In this video, I not only want to show you again how to implement this forecasting technique, but I also want to talk a little bit more about forecast accuracy assessment. Now we're looking at a different data set here. This data set actually spans 12 years worth of data from 2000 all the way through to 2012. And if we plot this data, which remember we should always do first, we're going to get this line right here. You see, of course, it's easy to make out a positive trend. And also there's a little bit of a squiggly up and down, which is in part actually might be attributable to seasonality, which is why, of course, this data lends itself well to the implementation of Holt Winters forecasting technique. Now let's jump right in and do just that. Let's get rid of this graph, and what I'm revealing underneath are the formulas that we can use to implement these calculations for Holt Winters forecasting technique. And we can simply read those formulas to guide what we need to calculate. Before we get to do that, though, remember the first thing we need to do is to seed the seasonal components. And the way we do this is we take the actual demand observation and subtract from it the average demand observation, of course, of the first year, which of course is the first 4 quarters in this case. So I get a seasonal factor component, a seed of negative 690 for the first quarter, and I simply copy this down through the remainder of the first year. And now I continue with the seeding exercise, turning my attention to the base level, and I seed this as the actual demand observation minus the associated seasonal factor estimate. Next, we see the trend component, which remember we simply start out with a 0. So now that we have done this, we can go ahead and calculate weighted moving average estimates for the base level, trend, and seasonal components. And remember, to do that, we first need to define our weighting factors alpha, beta, and gamma. I'll just pick some arbitrary values here for now, 0.25, 0.15, and 0.25. So with that being done, let me go ahead and start out by taking a look at the base level, which is alpha times the first way of estimating the base level is to take the actual demand observation in the current period y sub t and subtract from it the most recent relevant seasonal factor estimate s sub t minus p, where we call p stands for periodicity. That is 4 in this case because there are 4 quarters per year. So s sub t minus p, since we're in period 5, would be s sub 5 minus 4, which is period 1, or the seasonality factor of winter of 2000. So that's what we're subtracting here, plus 1 minus alpha. Now the other way of estimating the current period base level component would be to take the prior period base level estimate and add it to the prior period trend component. So that gives me an estimate of about 10,340 in terms of the weighted average base estimate for period 5. Now we'll implement similar calculations for the trend component, that is beta times. Now one way of estimating the trend would be to look at the increase or decrease of the base levels. In this case, we're looking at an increase, of course, so E sub t minus E sub t minus 1. That's one way of estimating the trend. The other way, of course, would simply to apply weighted factor of 1 minus beta times the prior period trend estimate, t sub t minus 1. Finally, we're getting to the seasonal factor. So here the weighted factor will be gamma, and one way of estimating the seasonal factor would be to take the difference between current period actual demand and the current period base level estimate, y sub t minus E sub t, or of course 1 minus gamma times the most recent relevant seasonal factor estimate, which again is C sub t minus p. So now I've started or implemented the weighted average calculations for base level, trend, and seasonality. And I can simply go ahead and copy these calculations all the way down throughout the remainder of the data set. With that done, I can now proceed to calculate my auto sample forecast. In other words, I can calculate my forecast for the year 2013. which would then be equal to, as we see to the right, the formula, the most recent base level estimate E sub t plus the most recent trend component T sub t. And now, of course, I want to make sure I'll add this the appropriate number of times, which will be the difference between the current period and the most recent period with an actual demand observation, which is period 52. And finally, I will add the most recent relevant seasonal factor estimate. And if I'm in winter of 2013, that will be that one from winter of 2012. So that gives me an auto sample forecast of 14,856 for winter 2013. And if I copy this down, you'll see I have my auto sample forecast for the remainder of the year as well. So with that being done, now let's take a look at forecast accuracy assessment. And that's something that we haven't talked about before. And it ties into those values for alpha, beta, and gamma, which recall I chose arbitrarily. Now, of course, I do not want to assess the quality of my forecast and the validity of these chosen values for alpha, beta, and gamma. Now, in this case, I have a very long time period, and that affords me a certain luxury. In fact, what I can do is I can implement these forecasts the way we just implemented them, and I can pretend I didn't have the associated demand observation. In other words, what I'm trying to say is let me skip the first 2 years and start in the year of 2002. Now, the reason I'm starting here, by the way, I now have for the entire preceding year estimates for the seasonal factors, and I have, of course, weighted estimates for the most recent base level and trend as well. So if I was in the winter of 2002, then my forecast would have been the most recent base level estimate, which was that of fall of 2001, and I would have added to it the most recent trend component, and I would have added to it the most relevant seasonal factor, which would have been that of winter of 2001. So you see, I would have at that point in time calculated an out-of-sample forecast of 9,938. And of course, I can do the same for the remainder of my data set. And now this allows me to evaluate just how accurate would these forecasts have been. And to do that, of course, all I need to do is take the actual demand observation and subtract from that the associated forecast that gives me the forecast error. And I'll also calculate the absolute value thereof. So now this will give me a means to assess just how good these forecasts actually are. So I'm going to go ahead and calculate the mean absolute deviation, which you recall is simply the average of all the absolute forecast errors. And I'll calculate the mean error, which is the average of all the nominal forecast errors. So now with that being said, I can figure out with this change if I change the values of alpha, beta, and gamma. So for example, what happens if I change alpha to, let's say, 4? Now you can see here my mean error of uncertainty goes down quite a bit, although my mean absolute deviation goes up. What I can do, of course, is I can use the computing power of Excel to find the values of alpha, beta, and gamma that will actually minimize forecast errors. So what I will do is I will use Excel Solver, and I will tell Solver to minimize my mean absolute deviation by changing the values of alpha, beta, and gamma. That's what you can see in cells B1 through B3, subject to a number of constraints. Remember, of course, that these weighting factors have to be between 0 and 1. However, prior research has shown that for all intensive purposes, you usually want values of alpha between 0.02 and 0.51. Likewise, beta should be between about 0.005 and 0.176. And finally, gamma should be between 0.05 and 0.5. So I've implemented those values as constraints down here, as you can see. And now if I click on Solve, what Excel will do is it will find those specific values of alpha, beta, and gamma that will truly minimize forecast errors or maximize forecast accuracy. In this case, in terms of the mean absolute deviation. Now, the one caveat I want to highlight, though, in terms of using this optimization procedure to find the best possible values for alpha, beta, and gamma in terms of minimizing forecast errors, is that we need a fairly significant amount of data to do so. And again, the reason being, I really wanted these 2 years worth of data, and that's because to calculate these forecasts, I would need a most recent relevant seasonal forecast estimate that is weighted, and that's why I really need these 2 years. In the first year, I have seasonal factor estimates, but those are not these weighted average estimates that I really want to use, that are probably better ways of truly gauging the degree of seasonality. So that's why I need to start with a data point beyond the second year. And then, of course, I want to have a meaningful amount of data to assess forecast errors over a long period of time, so I can really reliably estimate mean absolute deviation and mean errors and find ways of minimizing those. One other issue, of course, is that what do I want to minimize, the mean error or the mean absolute deviation? I could, of course, also try to find the values of alpha, beta, and gamma that bring the mean error as close as possible to 0. And in this case, of course, the resulting values of alpha, beta, and gamma might also be different than if I chose to minimize the mean absolute deviation the way I just did it here. This concludes this discussion of the Holt Winters method. Please watch my third video on Holt Winters, where we talk about finding the reorder point.